Hi, everyone. I'm excited to be here presenting. First of all, do people see us? I think there's a delay. I forgot that I always do this thing with the delay. I hope that people can see me. There's going to be something like 10-second delays. We are very excited to host Sam McDougle today, everyone. And a reminder to anyone who's joining us for the first time, the Learning Salon is a forum in which we come together and have interdisciplinary discussions. The presenter typically takes about 15 to 20 minutes to discuss. And, okay, good. I think now they see it. And then we ask them some questions, and then the audience asks questions. I want to remind you to be very mindful of each other. People are interdisciplinary from different backgrounds, but at the same time, we encourage people to sort of do their homework in terms of, like, you know, reading some stuff and helping others out if they know the answer to some question. Brad and Hanukkah in the chat will help to answer any questions that come up in the chat. In the meantime, there is going to be an ask a question button below. If you haven't used it before, please enter your questions there and like each other's questions so we know whose questions will go first. We will invite some of you on screen. Our goal here is to complement the writing tradition of science with discussions. So you don't need to know everything, but it's important that in the discussions, you don't come from a place of assuming you know things, but come from a place of asking questions when you don't know things. And we think that discussing science in an interdisciplinary forum is a different skill and an important one to form. So if you're an early stage scientist or a student, please feel free to ask your questions also in the Ask a Questionnaire. Okay. So we had a little discussion about who's going to introduce Sam before, because Sam is a good friend of mine, but also, in addition to being John's friend too, John was also on his PhD advisory board. He was his external, I guess, I don't know what the term is. Every university has a different term and I've forgotten. What's the term?
External adversary, I think is the term.
Wow. Friend and external adversary. So I guess John gets to introduce Sam. So John wins because in addition to all right. This is a moment. Go on, John. We had a little bit of salon banter, so go on.
Sam, okay. So as we have said before, we don't do the classical credential introductions, but Sam is an assistant professor at Yale. I was indeed on his committee. I have to confess that it's a little incestuous because, you know, Sam was with Jordan at Princeton. Jordan was with Rich Ivory. Sam was then with Rich Ivory. Rich Ivory did his sabbatical with me in New York, so it's all rather in the family, right? But I think what I would like to say is that it's really nice to see that you can come into the world of psychology and the broader notions of cognition from motor control. And of course, I'm biased, but I do think that Sam is very much in the tradition of bringing these two traditions together. And I followed his career since he was an embryo, and I think he's been exceptional already. And I'm very excited to hear about what he has to say at the interface of cognition and motor control. And there will be topics, I think, which have come up a lot in the salon so far. So I will stop there and welcome Sam to the Learning Salon.
If I may add one more thing, is that so in addition to what John said, Sam is very good at integrating reinforcement learning and cognition into the work, and in the tradition that John and Rich Ivory and Jordan have been having in motor control. So I really like that angle of his work. I mean, others do it too, but I think that Sam, especially after having worked with Ann Collins, really sort of brought this reinforcement learning aspect forward. And he also is a great musician. So for those of you who don't know, check him out.
I would say great's a relative term, but I'll take the compliment, Ida. Thank you. And John, thanks for the intro. It's great to be here. Thanks for inviting me. That was a perfect description. I don't really even need to give an intro now of what of what I'm interested in talking about, but I will anyway, so I can show some goofy slides. Can you guys see? Oh, you're seeing the whole thing. Hold on. Do you see that now in a nice square?
Yeah. John, would you mind muting yourself?
You know, I'll just leave.
I'll take it from here. Cheers, John. Good to see you. Bye. Okay. I'm going to give my premise here, and then I'll go into some details, and I'll try to keep it quick. I just first want to say I just love this salon. I've been able to make probably about half of them. I blame childcare reasons for missing the other half, but I just think it's been a lovely thing, and I want to thank Jova, Ida, and John for doing it. It's awesome, and there's no reason I think that when the pandemic is over, hopefully sooner rather than later, that this kind of thing needs to also end. So I hope that cheers to many, many more of these. Okay, so my premise here, you see my OSX menu? Yeah, I was having issues getting rid of that before, so bear with me. Hopefully there's no embarrassing notifications or apps. So my premise here, I'll just read directly, is that I think we should embrace what many would consider an inconvenient truth, that even in really simple learning tasks, thinking about humans here, we recruit at some point virtually every learning and memory system we have. So what do I mean by that? Well, to start, I think what we should think about in thinking about learning is kind of the object of study. And I would say the object of study in a learning salon is, one object of study is the learning curve. And that, of course, inevitably leads to the question, what's in this thing? What forges this thing? And what I want to do quickly today is be annoying. I think my role here, hopefully today, is to just be annoying. And so I'm going to be annoying by, hopefully not in my persona, but in my nitpicking of the kind of complexities that go into a learning curve. And so I'll start here with a pretty much well agreed upon annoying fact about learning curves, which is that they're not always curvy. Right? Sometimes a learning curve is more like a step, as I'm showing here with the man in the elevator. And this is not just true for things that are really cognitive, like having a kind of aha moment in some kind of exam or something like that, but even in really what people would call simple forms of learning, like Pavlovian eye blink conditioning, where an animal, let's say a mouse here, learns that environmental stimuli like a tone is predictive of an aversive eye puff. When the animal learns to exhibit a conditioned response, which is a blink in response to this tone, and if you average 7 or 8 mice together here, you get a nice classic power function learning curve, as you can see there in black. Okay? Now, of course, that's not really what learning always looks like, even in these simple tasks. So what I consider a classic paper by Randy Gallistil and colleagues almost 20 years ago, they went through a bunch of instrumental learning and Pavlovian learning tasks. In this case, this is an instrumental example, but it really works for all these tasks, where if you actually look at individual animals, you see something very much not like a power function learning curve, but something a lot more like a step function. Or I've labeled these two birds, the analog bird and the digital bird, because the one on the left, after many failures, finally sort of figured out some strategy of pecking, but had some nice variance around how many times they pecked for each conditioning stimulus. And the digital bird seemed to, almost exclusively either not respond or respond, right? And then sometimes multiple times. So there's these really sort of cool idiosyncratic strategies within an animal that to me suggests that you're not going to get far with an explanation that posited some sort of monolithic single learning process. All right, annoying thing number 2. This is maybe the most important one for what I'm going to talk about, which is that I don't think the learning curve also always reflects what we think it should or does. What do I mean by this? Well, the simplest way to describe this is that you might see behavior that looks identical between subjects or within a subject, between trials or between tasks or whatever, when really they could be being generated by dissociably different learning processes. And this is sort of similar to this idea of multiple realizability, or I would call it more kind of multiple psychological realizability. Another way to say this in a kind of a coarse fashion would be to say there's more than one way to skin a cat. That aphorism is kind of gross, but I think it's what I mean for sure. And then, of course, anyone who's in a comedy dork like myself Improv comedy has the tenet that whenever someone posits something during an improv, you say yes and, right? So if I were to ask you what's going on in a learning curve, I think the answer is often, and you say, sorry, process X, I think the answer is often yes and. And what do I mean by that? Well, I'll give you a quick example. So let's imagine an artificial agent here. I'll say Roy Batty from Blade Runner is our artificial agent, and we'll say that our human agent is the actor who portrayed Roy Batty, the late great Rutger Hauer. We'll assume he's human, and they want to learn a very, very simple task. Okay, let's keep it real simple and just say what they want to learn here is that a certain stimulus, one of those shapes, should be associated or will lead to a reward if a certain response to that shape is given. So maybe a button on a keyboard. Okay, these are the kind of experiments I'm talking about. And we can ask, all right, what would Rutger Hauer and what would Roy Batty do to accomplish this task? A simple way to model the AI version, we'll call it, of this task is as just a kind of vanilla, simple reinforcement learning process where over iterative trials, Roy learns the 4 associations. That creates some kind of learning curve. And of course, if you look at a human doing this task and you tinker with the parameters of an RL model, you can perfectly capture what the human's doing. And hey, look, we did our machine learning due diligence and we achieved human level performance with a very straightforward model. That's great. Is that really what we think's going on? Even in a really, really kind of off the shelf, simple instrumental learning task like this? And I don't think the answer is yes. I think the answer is no, because while there is evidence that reinforcement learning in some sense of the word is going on in this task, so some kind of iterative trial and error reward-based learning, my former advisor, Ann Collins at Berkeley, showed very convincingly, I think over a decade of work at this point, that you can also see very clear signatures of kind of working memory, short-term memory stores contributing to how people learn these types of stimulus responses, even in really, really simple settings. Another thing that, and this is a really nice paper from a group in Germany on the same task, that people do astoundingly often in these tasks is do actually deterministic hypothesis testing. In other words, they'll try individual actions in an order. They'll go left to right, or they'll say, I'm going to do this finger rule out, then I'm going to rule out the pinky, blah, 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 right? So people seem to go through this kind of probabilistically, this map of, deterministically, this map of different hypotheses. Finally, something that's very common in any kind of task like this, with ones with movement, is that you get Thorndike's sort of less appreciated law of exercise. So Thorndike had the law of effect, which is the undergirder of reinforcement learning, but he also had the law of exercise, which is that actions that happen tend to be more likely to repeat it, kind of regardless of the outcome. So perseveration is one way of describing that. And of course, there's a lot of literature on other processes and tasks like this. If you make them slightly more complicated, make them slightly have some kind of sequential dependencies, you can get what's called model-based planning. There's certainly evidence that people sample from episodic memory, even when they do very, very simple instrumental learning tasks like this. So we've got 5 or 6 different processes going on, in this case, in what we would consider a task that we would hope would isolate a single process. So that's a problem. This was also true for motor control, as John mentioned. That's mostly what I've cut my teeth at as a psychologist. It's kind of lonely sometimes doing motor control, but I think hopefully that's changing. But even in really kind of canonical classic motor adaptation tasks where people learn, let's say, to counteract a perturbation between their movements and some kind of sensory feedback, in this case, maybe a rotation or something like that, you can model people's learning very, very accurately with a really simple kind of linear dynamical system, at least if you're just looking at one block of learning in this simple task. So that looks like a good candidate for thinking about a singular learning process that drives visuomotor adaptation, in this case, learning to reach in this other direction over time incrementally. Of course, if you just ask people what they're doing in these tasks, which is something that John and colleagues and Jordan Taylor at Princeton did several years ago, they're doing something. They tell you that they're doing something that's not just, what do you mean, I'm reaching at the target? They're doing something more interesting. You can actually quantify that kind of qualitative data, and you can dissociate what we would call explicitly accessible, intentional decisions about how to move. It's a loaded term, but I'll use it here anyway. And maybe a more implicit form of learning that's not consciously accessible. But then even you can subdivide those two divisions. So even this kind of implicit learning seems to be mostly made up of cerebellar recalibration. I won't go into details here, but there also seems to be reward sensitivity in that system, suggesting that There's an underlying RL process that's routine that's running. And then there's also the law of exercises in there. Again, people just tend to create little, do little repetitions of movements, even if they weren't rewarded or didn't have rotations or anything. Moreover, if you look at this kind of explicitly accessible hypothesis testing type stuff, there's a lot of elements there too. People will take a verbal instruction and translate it into a motor plan. So that's an interesting process. People seem to be doing kind of intuitive physics in these tasks and thinking rotationally about how they should move in a kind of intuitive sense, as if they were doing mental rotation, which is a classic cognitive psychology finding from the 70s. And then also, there seems to be kind of evidence that I think is pretty strong, even though it's still developing, that if you look at long-term retention, even after a small amount of practice, people seem to kind of sample from an episode as if they sort of remember, oh, I think I have a good way to do this from my episodic memory of how to do this task. So
I'm sorry.
Yeah.
Do you mind going back to this last slide and just explaining the task? Because I don't think the audience is familiar with John's.
Yeah, sure. Sorry. Yeah, that's a great point.
And maybe just
Yeah,
very quickly,
the
the
task,
X and Y axis.
Yeah. Thank you, Ida. I apologize. So the task here is really simple. People just try to reach to a target. They can't see their hand in this case. They get some kind of visual feedback that's supposed to represent their performance in the task. In this case, like that red cursor. And what you do is you just manipulate the relationship between their movement kinematics, or the angle of their movement, let's say, and the angle of that feedback, so that to actually hit the target with the cursor, in this case, you'd have to reach at an angle. Okay, if that makes sense. So the y-axis here would be the angle of your hand relative to the target. In other words, where you should move to succeed in the task. Okay, so that's what I mean by the y-axis here of angle. Sorry, that wasn't clear. Thanks, Ida. So the idea here is that when you look at someone's data in purple, which is where did they move to succeed in this task, you can dissociate their intentions of where they wanted to move from where they actually moved. And the difference of those two things you would call learning that they're not aware of, right? They're not actually moving where they think they're moving because there's this underlying implicit learning process, if that makes more sense. And so this should make us think of what in cognitive psychology we call the taxonomy of memory. I've thrown learning in there because it's a learning salon. And I think when we think about, I think this taxonomy is useful. I mean, I have some issues with where skills is on there, but I think it's a useful way to organize our thoughts about different learning processes. But I also think our assumptions about this taxonomy should be questioned. So often, when we think about this taxonomy, we sort of think as experimentalists what tasks would probe which individual process. So you might imagine if I want to talk about the learning of facts, I would have some task I that would probe the learning of facts. If I wanted to test a priming effect, I might have some task J that would produce data that would look like a priming effect, and same for something like classical conditioning or Pavlovian conditioning. But really, if you get dirty in the data, it really seems like for many tasks, not all of them, but for many tasks, you really don't have this clean sort of taxonomic separation. It's actually a messier sort of mix of learning processes that contribute to behavior, even in tasks that you think wouldn't have those annoying other processes. And so my joke here is I think you could kind of take every chapter of William James's principles and kind of dump them into most tasks. Like there's an attention element to each task, there's a memory element, there's this habitual element. And I think we have to be careful to say that a given task, whether it's in a machine learning agent or in a human agent, is giving us some kind of purified, isolated learning process. All right, annoying thing number 3. This is the last one. I think this one's kind of trickier, but I also think as important as the other annoying things, which is that not only are there multiple processes contributing to the learning curve in a general sense, but there's also a dynamics to that. In other words, there's different processes that contribute to different points along the learning curve. This was made clear by a lot of theorists and a lot of experimentalists. Gordon Logan has a nice theory of this idea that you transfer from algorithmically thinking about a task to actually just kind of retrieving a memory for an exact instance of what you should do. So for an example, if you're learning how to read sheet music on piano, any of us as kids who took lessons might be familiar with the pedagogy that you should anchor your thumb on middle C and then translate distances between your fingers on the keyboard to distances, vertical distances on the staff. That's an algorithm, right? A simple algorithm you can implement to quickly get decent at sight reading. And of course, anyone here who is a piano expert doesn't do that, right? Sight reading is a qualitatively different thing once you've practiced it. And so those two different points on the learning curve really are representing qualitatively different processes. And I think that's really a critical and sort of underappreciated fact. I would call it a fact. And like I said, there's been other theories for thinking about this idea of kind of stages in Fitz and Posner's book. And then I have to put a quote here from John, just so I can flatter him. In his recent really nice review about motor learning, he and colleagues have a nice quote here that even if the endpoint of learning is this procedural skill, the way you get there, right, is very much a cognitive endeavor. And I think that's something that is easy to nod your head to when you read it, but I think is really has a lot of implications for how we study learning. And just to make a little comment here, I do think if we focus too much on what a converged network is doing, we're often thinking very much about the asymptote of learning, right? So after our network converges, and we look at the behavior and compare it to humans, we're studying the asymptote, I think, for the most part. Okay, so what are some issues with this framework I've given? One is I haven't really told you how you define a separable learning processes, right? So I've said that I think there's these separable processes, but I haven't proven it to you in any particular way, nor have I given you a systematic way of defining multiple processes. I think there are ways to do this. One would be formally. So if you have a way of writing down what a learning process is, and you can gesture or prove that two different models are separable in that the full space of predictions they make, regardless of their parameter settings, are not identical, then you could argue that you've posited potentially two processes. I think a more kind of tricky issue, but one that's I think fundamental here for me, is if you can separate them psychologically. This is tricky, and I think I can sort of put a finger on why this is tricky. If you look at definition, in this case in Ashby and L, a really nice paper in 2002, they described at the psychological level trying to dissociate learning processes, and it sounds a little circular, right? So at the psychological level, to qualify as separate systems, S1 and S2 should postulate different psychological processes, right? That doesn't totally get us all the way across the finish line. And then finally, there's the physiological question. This one I think might be easier, right? Learning systems that seem to be implemented within an animal or an agent in totally different, well, I guess not agent was tricky, but in an animal in totally different places in the nervous system is a clue that they're different learning processes. And I think things like, if you've heard of complementary learning systems theory, I think is a great example of how that can play out. And finally, the last two issues, I think one other issue is, of course, if these processes interact with one another, maybe competitively, maybe cooperatively, is interaction the exception to the rule? I think there's a lot of evidence in favor of both. And then finally, why would we have multiple, the normative question, why do we want multiple learning systems to create essentially the same learning curve? I think this is a tricky question. I think you can find ways where it's optimal sometimes to have all these different processes. And I question that optimality sometimes, because I also think we should think of the brain, as Gary Marcus put in his book Cluj, as this sort of stacking of natural technologies over time that doesn't necessarily have an obvious normative behavior. And finally, I'm going out of my lane here to talk about machine learning, but I do think, something I think I've noticed as a total outsider of machine learning is that there's an emphasis on minimalism. So there's this emphasis on having as few learning rules as possible, that complex behaviors should emerge from a really simple system that you make, minimal system, and KISS, keep it simple, stupid, seems like an axiom. I would argue that I think maximalism is maybe something useful to think about, which is get a little messy and think of learning as this kludgy thing. There's lots of different subsystems. You can ductate them together. That's what evolution did, I think. Maybe optimality is overrated. I think that's a controversial but important thing to question. And then also maybe think about other approaches to AI altogether, which is maybe thinking about things like symbol manipulation. So with that, I will shut up for a moment and unshare my screen. Did I succeed?
Yeah, thank you, Sam. I don't know who wants to go first, but I'm more just confused what the main point is. I don't think I'm clear about, you're muted, John. You're still muted.
I think you should go first.
It's just clarification questions for me first. And then based on what I understood, I wonder whether that's the mainstream idea of learning already. So is the point that there needs to be multiple learning systems, and that seems to have been the mainstream idea for 30 years or more. So that's what I'm confused about. So maybe it's in motor domain, it's different. So yeah, I think I'm just confused.
Yeah, so am I being too obvious, I guess, is the question. I mean, I actually don't agree. I think that the mainstream
I'm
thing
not saying being too obvious. I really didn't get the main points. I genuinely
well, I
didn't.
think, yeah, well, I don't think I made one main point, but one issue I have is I do feel like for decades, the allusion to multiple learning processes has been the dual systems idea. Mainly that there's a like the fast and slow, or the model-based, model-free, or this and that, and in that sort of two-dimensional space. And I think that, you know, you can find evidence that a lot more dimensions need to be added to that framework. So that's specifically true for RL. I know you agree with me. I don't know if that's necessarily mainstream, that RL seems to be stuck on a dichotomous sort of approach, and that there's a lot of ways forward of making that more complicated. Another thing is I still think for something like DQN's learning Atari games, there's still this minimalism approach where you, even if you add an LSTM or something like that, you still kind of have a somewhat stripped down one or two learning processes driving learning. So I don't know if that's that accepted, that you should lump on all these other different processes. I mean, I don't even know if you should. If you're not interested in mirroring human learning, then I don't think you need to bother. But yeah.
So one thing that I want to say is that when in 2005, Nathaniel had that paper with Peter Dayan and Yael, and they were talking about model-free and model-based being combined, that was an introduction to RL for cognitive scientists, perhaps, but RL models are not exclusive to using two. In fact, if anything, our critique of many contemporary models is that they are way too maximalist. So I put a link to, for instance, Agent 57 from DeepMind. The DQN example that you mentioned from the 2015 NE paper, the first Atari paper, DeepQ Learning, that one is the most basic of them all. It was like a proof of concept. Everything ever since has been, you know, first add prioritize replay, then add this, then add another component, various components. And if you look at the architecture of Agent 57, if you scroll down, you will see that it actually even has a DQN of 2015, and it scrolls down to the R2D2 that is added, and then Never Give Up that is added, and Agent 57, and you can see how many modules they have added. So as you can see, if you can see the modules, I mean, I can share my screen if that helps with everyone else, because I think it's an important point to make.
Yeah, why don't you share your screen?
Yeah, that might be a better idea. Let me just share my screen here. Okay, do people see my screen?
I can see it.
1 second. There's something on my screen. Okay, so this is the architecture of the Agent 57. So it starts with the DQN of 215. Then it has some improvements on it, and then the R2D2 of 2019. It has, like, you know, the short-term memory. LSTM and GRU were added, but LSTM is no longer sort of the, you know, transformers have taken over now. And LSTMs were introduced already in the 90s. They weren't a new thing either. Exploration, these many things were added for the Never Give Up in 2019, plus episodic memory components, and then a meta controller with multiple approaches, and all of them together led to Agent 57, right? So this is definitely not a dual system. This has an archaeology, it has like a, you know, background, and it is a little bit, what, 57? What are you asking, Danielle Finol? I don't understand what you're saying. So the link to what I'm mentioning is in the chat. So this so this is the thing that I'm not quite sure about. This is the state of the art of the agents that are solving things, right? The first paper in any situation, like the 2015 paper that you referenced, the DQN, even that one, it's like having a lot of different layers, right? So even that one is not as simple as, for instance, a regular reinforcement learning. But there's so many components added to it already. Double DQNs had 2 of them together, prioritized replay of David Silver, distributed dueling, has so many things were added at each level. And the general components are, you know, the DQN parts, the short-term memory, the episodic memory, exploration, meta controller. They have even made this kind of larger scale categorization and smaller, finer scale, right? Which is why and this is empirical RL, in the sense that there is a set of problems, and let's just put things next to each other on the basis of some intuition from neuroscience, from cognitive science, or just whatever works. Some of them improved based on whatever works. We just put some components, right? So it does seem like the maximalist approach. If anything, it's a little less principled than we would like. If anything, we have too much maximalist approaches for solving things. In practice, the ways that RL is used. And so, for instance, theoretical RL comes to, like, you know, say, all right, let's do this in a principled way and see how we can sort of keep this going. You look at transformer papers, it gets even more complicated in terms of the maximalist approach. So I'm just going to stop sharing. But that's the reason that I'm.
Do we lose Ida?
I think she stopped sharing her whole self instead of just the screens. You know, like at the end of the put your left hand in, put your right hand in. She took her whole self out.
Yeah, I'll text her.
She knows I'm adding her back.
Okay.
Maybe you should have sang that song. You're the musician here.
Sorry about that. So I'm a little confused. That's the reason I'm confused. I'm genuinely confused because the premises don't seem to fit my understanding of the field.
Well, I think you, again, like I think that you partly framed all those additions of the episodic memory and short-term stores and all that stuff as sort of at the end of the day, it seems like too much. It seems too maximalist to you. Right? That seemed to be what you were saying at the end.
Oh, I'm saying in this, but no, I'm saying.
Because I love it.
No, I'm putting it against your claim. Your claim was RL is dual systems only. And I'm saying, no, RL is very maximalist. So that's the first point.
Fair enough. I mean, fair enough. You did show, you know,
but go on.
No, I mean, that's fair. I'm maybe you're saying I'm straw manning an argument that ended in March. When did that paper you just put up there? March 2020. But I mean, like, I don't think it's that accepted that there's this necessarily like complete kludgy mess of processes, at least accepted as a way forward for thinking about learning in humans. I mean, I just think it's not, you know, if you agree with me, that's great. But I think often you get a lot of pushback when you try to tell people yes and about all these learning processes being involved in tasks. And I think, you know, the example of people over parameterizing or things like that is one thing, but the example of lumping on different processes that we know for a fact are at play when humans do these tasks. I mean, I don't see the problem with it. Maybe that maximalism should be a principle.
So to be clear, this is not necessarily a human-like way of solving the problem. So my critique of that work. So I think that here is the thing. Your critique is of classic cognitive scientists and psychologists who don't like models that have more than 2 components maximum. But when you use the term RL, my repertoire of RL is the entire world of reinforcement learning and not the way that it's used in a couple of labs in cognitive science, right? So I think that's where the definitions, and this is great. This is exactly why we have the salon, for the different sort of multidisciplinary perspectives. So I love that this came out. And the second thing is maximalism. There's two ways to approach this. One point is, hey, it's a complex system and we need to take into account more than just optimality and just reward maximization. And I'm actually working on projects related to that. I agree with you. I think we even need to take the ecosystem into account. But then there is another point of just putting components on top of each other and see when it works, right? That is an empirical approach that would solve a problem when you have an engineering problem. You're like, hey, we want something to solve more, for instance, Atari tasks, right? Then you can do that until you solve things. And yes, that paper is 2020, but the papers before that, that were the components, and each of them were an improvement on the last one that were combining things. They date back to 2016, right? So since 2015, where the DQNs came out, this was just the trajectory of the example of DQN that you provided, right? There were a lot of the branches that you saw until now, all of them came together for this agent. I think that there's maybe 2 points, and it is actually perhaps worth noting your point. Maybe if I imagine what you were saying as like, it seems like there's 2 points to that argument. First, maybe the use of RL in psychology and neuroscience has been too simplistic. And second, maybe the maximalist use of components in RL in machine learning is a little bit less principled than we would have if it wanted to be human-like, because it seemed like that is, I guess, the two sides of the way that we are seeing things, right?
I just want a clarification. When you say, no, I agree with that last point. And when you say that all those elements they added in the Atari 57 example, that's all RL too. And my definition is just too narrow, but all that stuff is RL. I get kind of confused. So are we just going to say then that is the answer just that all of these processes, because they could be implemented in an agent that is built on principles of RL, is RL too? I mean, then I just get a little bit like, okay,
well,
so
learning is its own field, right?
No, yeah, I know, yeah. But I just think that, I think we have to be clear that if the definition of RL just becomes learning.
No, it's not. For instance, various kinds of machine learning and supervised learning are not reinforcement learning.
Yeah, no, I know, yeah.
Right, so it's not the same.
Yeah, no, I know, but that example you gave me had all those elements of episodic memory and this and that. So is that episodic memory is just there to serve RL in that case, right?
Well, episodic RL is a particular approach in RL that has existed. So
sure, right.
The term, maybe you're using the term reinforcement learning different than me. It's not just a model free or model based, just like simple policy, right? It's basically a framework within which you could write algorithms, not predefined and prepackaged, new algorithms in order to solve particular learning problems. It so happens that some of these particular learning problems are problems that mice solve or humans solve. And it so happens that of the algorithms that solve those particular learning problems, some of them would also look like they have human-like or rat-like representations, and some of them won't, right? So there is no guarantee that any RL solution is going to look like the solutions that humans use for learning. So there is extra work needed to be done for RL algorithms to be biologically plausible, whether it be a rodent algorithm or be it a human algorithm. There is no restriction on how many components one can use in them. But if you want it to be human-like, it's not enough to chase a benchmark. You might need it to have, for instance, what we're doing with navigation Turing test. Having human judges look at the behavior and say how human-like it is, that's one way. And another thing is, and then training maybe a classifier to be able to judge that. Another thing is, you want to look inside under the hood. What kind of representations did it learn? What kind of processes is it using? Are these the kinds of processes that we can find in human brains or human sort of components? And if not, it's important to dissociate all of these. I feel like there is an interesting point to be made that you're making, and I agree with it. I've seen what you're describing in cognitive science and psychology departments, what you're describing as kind of like expecting things to be maximum a dual system. So I totally see the minimalist point that you're making for the use of RL classically in psychology and cognitive science. But its meaning is not just classical conditioning, or, you have reinforcement learning as a framework for learning, even in absence of rewards. It's a much broader theoretical framework. And so I think, yeah. So does that make sense?
Yeah, I'm okay with, I'm okay if you allow the thing you're talking about, if it's reinforcement learning in the machine learning community, to expand itself to capture all those other learning processes and do justice to what we think those processes are in organisms, then I think that's fine. Yeah.
Can I try to weigh in here a little bit? So, I read your very nice paper, The Role of Executive Function in Shaping Reinforcement Learning, and I think in there you and Anne and Milena point out that there's a lot of kind of classically defined cognitive mechanisms that are not trial and error learning, that are, say, working memory, that in cognitive science is not typically thought of as part of the reinforcement learning process. And you're saying they're different. I think what you're saying is they happen in different parts of the brain. There's a different physiological process. And historically, at least in cog sci, people thought of them as different things. And what maybe Ida is saying, and I think you agree with, is that you can leverage these different cognitive processes to learn more efficiently. And in empirical RL, people have been doing that. They add in working memory or all this other stuff, and it's working. And what you're saying is you're advocating for people to do that more and more in neuroscience, because you think that actually reflects how humans are doing learning. And they leverage all these additional processes. And that is despite the fact that, at least as I understand your argument, that in the kind of dominant view in cognitive science, these additional processes aren't part of the model. Is that right?
Yeah, well, I mean, I think you got at attention, which is that the interaction of executive function and RL. I mean, again, like what Ida was talking about, I think you can, if you want to talk about the interaction of, let's say, working memory and reinforcement learning processes, and focus on the fact that there seems to be evidence that working memory can contribute to RL. In other words, you can have a prediction of what's going to happen in working memory, consciously accessible working memory, that can actually influence downstream reinforcement learning computations. And I think Ida made the astute point that, well, you could still think about that in the RL framework without having this very simple definition, which is that RL is just TD learning and cortical striatal loops. I guess, Ida, you're worried that I may be narrowing the definition to that, right? And I think it's perfectly reasonable, I think, to expand it if there's an interaction with working memory, for instance, to say, okay, part of the RL process involves this other system. But I still believe in borders. I still think there's borders between these systems, qualitative borders and formal borders. And so if we want to lump everything into RL, that's fine, but as long as the borders are clear.
I just want to add to that one thing, that there was a paper, and Tom Griffiths was one of the authors. I forget who the other author was, at CogSci, where they used the reinforcement learning framework for working memory. And they're not the only ones. So together with, we just had a paper together with John Cohen, Ken Noren, and Rick Lewis and Satinder Singh, where we used the reinforcement learning approach combined with the Bayesian approach to look at optimal integration of episodic and working memory to solve, for instance, prospective memory tasks, which is the ability to remember to do something later while you're busy doing something now. So I do think that there are more complex approaches, but I agree that traditionally psychology, behavioral psychology focuses on dual systems as opposed to multiple systems at the same time. So we want to look at complementary learning systems. We focus on separation versus integration, the associative versus sparse learning at one time. And then another time we focus on working memory versus episodic, but maybe we compare these. And I think part of it might be because of the limits of our experimental analysis. Like if you want to run ANOVA tables, how many conditions can you have? So that might be the reason for the psychology studies to focus on things that are dissociable in 2x2, a maximum 2x3 kind of studies, right? There are limits to our approaches. And I think that there is a good point to be made. However, the nice thing about that, I think maybe John has more to say about this in dissociations, is patient studies, which I know you have done as well, Sam. And similar to those patient studies are ablation studies in neural networks and RL agents, where you have different components in your algorithm. You knock out one part and see how the algorithm behaves. And then you say, hey, look, this working memory component that I had in my algorithm was necessary because when I knocked it out, it can't do this thing anymore. But this episodic memory component thing, when I knocked it out, it could solve things in the short run, but it couldn't solve the long-term things, maybe. I don't know. Like, you know. So I think that there are ways of, even when you have a maximalist system, to dissociate certain components by either having patient studies where somebody's hippocampus or prefrontal cortex is damaged, or having ablation studies where you knock out parts of the maximalist sort of component and see what it fails to solve. Yeah.
One tiny thing I agree, and one tiny thing I want to add to that, though, or maybe poke at a little bit, is you mentioned adding a working memory component to your RL system. And I guess to me, it's like, I'm trying to argue that working memory isn't a component on top of RL. Working memory itself can generate a learning curve without necessarily using, right?
I said the learning, the working memory component of the algorithm. So there is a bigger RL algorithm. Different parts of it are comparable to episodic memory approaches to learning, or working memory, or some other part. So the component of a bigger algorithm, not that it's separate from RL. I don't think that it's separate from learning. So I think we're on the same page about that.
Are you happy, sir?
Are you asking any more, Jovo?
I have a question.
Go ahead.
Oh, am I not?
I wanted to say I don't have a question, but go on.
Okay, I just have one comment to make, and I think I would like Ida to help me with this one, if possible. Happy birthday to you. Happy birthday to you. Happy birthday, dear Sam. Happy birthday to you. Can you blow out the candle from there? Wait, you're muted.
Perfect timing. Your video just shut off halfway through your song for me.
Should have been
So I'm looking
audio.
at a blank, blurry screen. But thank you. Thank
I'll
you.
blow
all.
the candle out for you and make a wish on your behalf.
We put the question first so that the surprise is larger for the cake.
Yeah, it's perfect. Thank you. Oh, look at all the nice stuff in the chat.
Yeah, I don't really have a question. I just want to sing happy birthday.
Thanks. It's nice to celebrate with you all, even though I'm alone in my office. Physically lonely, but digitally communal.
Lonely but not alone.
Yeah, exactly.
I am not going to eat those cupcakes. But if you would like
Just
some,
send
I
them
would
over.
happily send them. I tried to find your mailing address. It didn't occur to me you'd be in your actual office. I could have sent you cake to your office.
You could have surprised my partner and my son. They would have liked getting a random cupcake.
You know, the white pages didn't have your address as far as I could tell. So.
Oh yeah, I'm not in there. No, I'm off the grid.
Yeah. So okay. Anyway,
Thank you.
That was my main
That's so
question.
sweet.
I don't know if John has some
thank you.
questions.
I'm sure he does.
Well, not really. I mean, I just wanted to sort of defend you, actually. First of all, there are a number of things I want to say. Before, you know, the sort of implicit idea that the cognitive neuroscience psychology literature is stuck in dualities and the AI world has long since let go of that, I take a little bit of exception to, but we'll talk about that in a minute. I do think you're right that there is a problem. If you look at the textbooks, if you look at what's taught, if you look at the Larry Squire diagram, which is still taught, right? If you go all the way back to the Greeks, you have techne and episteme. You have the intellectual and the anti-intellectual. You have the practical and the theoretical. You have the procedural and the declarative. These dichotomies are very powerful. Right?
The hot and cold. Don't forget hot and cold.
So, the dumb jock, which I've written about, that athletes are dumb and nerds are not. So there's a deep bias going back to the ancient Greeks, that there's something different about doing something practically procedurally versus doing something declaratively and theoretically, right? So you're absolutely right. That is a rampant notion in the culture, and still, I think, in neuroscience and in psychology. So I think you're right. If you look at people, when it comes to your notion that there are simple learning rules, and, Ida is using RL, actually Tom Griffiths was on a podcast about a year ago where he said RL is not really a theory, it's more of a framework, right? It becomes more bigger, right? So Ida uses it in a way that I think is more inclusive, but I don't know why it keeps getting allowed to be called RL all the time. Just call it L, right? That's what I would call it, L, right? Which I think you're saying. And if you look at people like Rich Sutton on his website, right? He calls it the reward hypothesis, where he literally says on his website, I will quote, just give you the quote from his website. All of what we mean by goals and purposes can be thought of as a maximization of the expected value of the cumulative sum of received scalar signals or rewards. David Silver at DeepMind at a meeting in Japan said, reward is enough, right? So in other words, it's not Ida's view, but you're completely right that there are people who think that you can frame everything in that way, right? So it's not just us in psychology and neuroscience that are just lost in simplicities. It's true across many.
Sorry, I need to interject there, because there is a difference in what it means when, for instance, Rich Sutton says that, and the way that you interpret it verbally. So first of all, it's not all learning, because there are particular kinds of learning in machine learning that are not reinforcement learning. Secondly, the framework of reinforcement learning works on the assumption that you're maximizing some cumulative reward, yes. However, there are other kinds of assumptions. For instance, right now we're submitting a paper on interaction-grounded learning, where you don't know what the reward signal looks like, and you have no idea. Nobody externally is going to define it for you, so you have to ground it in interaction. There is so much work in intrinsic motivation that we're actually on that chart that I showed you, where the agent has to come up with some internal representation and use that as a reward.
I'm just not interested in hearing the word reward all the time.
So that is the point. It's not just a word. It's not just semantics. It's the way that you would write your equation. So the whole point is, this is a framework in which you find some way of chasing rewards. Now, that reward doesn't need to be defined as something that's external, like a classic condition, an example of like a bell and whistle, dog and food. It's basically, it can be something that is an intrinsic representation. It can be a structure you're learning. There are simple versions of it. There are parts of the reinforcement learning framework that is not like that. And as to the question of why not just learning, there are other learning approaches in computer science, many of them that are not reinforcement learning. They're different approaches.
No, I'm aware of that. I'm just saying that there's a slight total, if reward can take on and morph into so many different versions of itself.
No, John, that's not the point. The point is not that the reward can morph into everything. It's a particular framework for learning.
Right, okay, that's fine. And I'm just saying that that's fine. All that's going on here is that it may be that real life ecological tasks can never reduce to any single learning system. I think the point that Sam's trying to make is that maybe in real life, everything is made up of at least 2 learning systems, right? That's the kind of interesting point, right? That there is no such thing as a task that can be captured by any given way of thinking. I think that's what's interesting, is maybe that's true, that you just can't capture it without having 5 learning systems, perhaps. That's what's kind of the subversion here. And I think that's quite interesting, right? That might be the case. Now, and what is, I think the point being made is that if a visuomotor adaptation task, or these sort of Mickey Mouse-ishly simple tasks in the lab, are already horribly contaminated, then it may well be that the ecological world that is more human-like is so contaminated with so many things that we're never going to be able to approximate it with any given framework. Now, that's how I'm taking what you're saying, Sam, is that there is no single framework to look at ecological tasks in the world, because even the simplest ones are hopelessly contaminated. Now, that's a slightly different viewpoint, and I don't think that that is the normal view in the textbooks in the world, because we'd like to think that we can reduce down to assays that are fairly pure. Right? Now, maybe some are, but for the most part, it's hopelessly messy. Now, if maximalization and messiness are not synonyms, that's another conversation, but I'm sympathetic to the idea that human behaviors are so messy that they can't be approximated very easily. And that's interesting to me. Whereas benchmarks, things like chess and Go, as I've said before in this program, I don't think those are really human behaviors. I think those are abnormal torture games for the human brain, which isn't really meant to do them, right? And that's why we consider them so difficult. So anyway, I think that's the kind of point you were trying to make, not that you were attacking any given framework, right? I don't think you were. But I think, yeah, that's my point there.
No, that's a helpful and superior echo to the point I was trying to make. And I think, Ida, to your point about bringing up something like Atari 57, I mean, I do think that if we expand I won't say push the goalpost, because that sounds like I'm being rude, but I mean, if we keep expanding the boundaries of what a specific framework incorporates, then maybe we can get to a point where, John was saying, I'm arguing that we can't do it with one framework, and I sort of was arguing that. And I think if we take one framework and allow it to Pac-Man up all the other frameworks into this kind of giant kludge, or this giant, this giant holistic messy system, then that's good. That's kind of my point, is that the hopelessness of studying an individual doing a task in the laboratory is because you need more bigger, robust, multiple frameworks to be glued together.
So one thing I'm noticing, and maybe I'm way out on a limb here because this is far outside the domain of my expertise, but it seems like this maximization thing is arguably, people say, like, this set of procedures is sufficient to get some particular behavior or performance. And the minimization approach seems to be more inspired by saying this procedure is necessary, or you'd hope it's necessary because it's so simple. Nothing simpler could actually do it. You try to find the simplest thing that if you have it, then you get this behavior. So maybe it's a difference in focus on whether you care about necessary or sufficient components of this overall learning system, and those have different criteria for whether to include them or exclude them. What do you think about that?
The necessary sufficient question? Yeah, I mean, that's like, yeah. That's the key question in biology, right? So when you do like an optogenetic manipulation of a specific brain area in a task, then your goal is to show that system is necessary and sufficient, right? And so I think, like, if it's the case that doing a simple stimulus response task, I don't want to, my whole point of bringing that up is I don't want to cage myself in here and say that, okay, for example, if you do eye blink conditioning in a ferret and you decerebrate the animal, you completely remove the cerebral cortex and you leave the cerebellum and the brainstem and of course all the trigeminal nerve and all that, and you do eye blink conditioning in a ferret, you get the full conditioning behavior. You get it. You get the whole thing. You get the learning signal, you get the conditioned response, you get the input of the environmental context, you get the input of the error signal, you get the whole thing right in there in the cerebellum of the ferret. And so that's like a classic example of like necessary sufficient, right? And that also suggests that, to really properly isolate that system, and to prove it to someone, then you need to remove the entire cerebral cortex. And I think that, like, that's a powerful demonstration, but it just goes to show also, like, if you're going to, in a human, if you're going to try to obviously you're not going to do the same thing, but I do think that I do think that you're going to find very quickly that attempting to isolate a process, even with a lesion patient or something like that, and prove that it's sufficient to do the task, good luck, I would say. And so, in the end of the day, I think that's a tricky route. Oh, John just pulled an Ida and quit, unmuted and quit at the same time.
He'll be back.
The buttons are close to each other. Sometimes your mouse just slips for a second and then you're out. He'll be back.
Who knows what he's doing?
Actually, he might be here. I don't know why he's not in. It says mic muted. It doesn't say that he's totally out.
Should we take some questions?
I just want to say one thing about, so Sam, the example you provided was again a conditioning example. Yeah, I'm just gonna note that.
I'm biased.
Yeah, and I think that might be the problem. And or not your problem.
Well, I mean, it's complex the other direction, right? So HM notoriously, and John would echo me here, I'm echoing him. HM notoriously actually was pretty bad at learning motor skills. If you really properly look at at reports about how those tasks worked and things like that, right? So in the other direction, you have, a specific task even is misdefined as undefined as being whether purely procedural or not, right? So rotary pursuit, what HM had to do was just kind of keep his finger on a rotating disc and maintain a target, right? And as John has described in many of his papers now that he's back, the textbook story about HM and motor skill and procedural learning is not correct. It's just not exactly the truth. And so, yeah, I think the boundaries. So that's you're gonna tell me you're probably gonna rightfully tell me that's probably also another kind of simplistic conditioning style procedural task, but.
No, I don't think that. I think it's a great example. I think that the inability to understand the HM experiments properly, you're absolutely right. I mean, I even ended up having a back and forth with Larry Squire about it. I think is because there is as you said very nicely when you showed the asymptote, we're interested in the proceduralized endpoint. We're not really interested in that messy meaning declarative beginning. And I think that one of the reasons why we're still stuck in this dichotomy, I think Ida's right about a lot of people in psychology still thinking this, is because of the HM story. It's just been consistently misunderstood. And I think it's problematic. So I think you're right about that. And isn't it ironic that the kind of task that was used to make the HM case ended up on more close dissection to be fully contaminated by the declarative? I mean, the ironies multiply under the sun. I mean, it's delicious in a way. But it is a problem. And I think that it's going to take some time for it to go away, both within the neuroscience community and even culturally. The dumb jock idea is very powerful, right? And we have to get rid of it. And that's going to be because every single task that we care about, whether it's basketball, or chess or mathematics, are completely combined by many, many, many conscious and unconscious systems. And it's interesting what the lesson is to be learned from that. I'm not sure. But anyway, there must be lots of people interested in questions.
I just want to say one thing, though, that the question of, for instance, dumb jock or other kinds of associations like that, this is more, I think currently at least, it's more analyzed in terms of word embeddings, not in terms of some dichotomy, at least in machine learning. You think about NLP, you think about some kind of a word embedding and the associations and the amounts of times that you've seen things associated in your culture. So if you frequently see these associations, then you might make those associations. And it's not a dichotomy per se, it's multi-dimensional vectors of associations. So I think in NLP, at least, that's the perception is not that this is a dichotomy, but that some words have certain kinds of associations due to the frequency of appearance in culture. And another thing that I wanted to say to Sam's, notion of Cluj is that some of these deep learning approaches, they are like that. They are a Cluj solution by putting every component that I can next to each other so that I can solve the problem, right? Other ones are, for instance, my versions are all about how can this be human-like behavior? In addition, how can this be in human-like representations? How can be this a human-like algorithm? Which takes longer, it takes a lot of time to analyze it. It takes time to design the experiments. It takes time to come up with some constraints for what does it mean to be human-like? What is a human-like behavior in navigation? For your case, it's motor reach, but in our case, for instance, it's navigation. So it requires planning at different scales. It requires, managing your velocity and many things. One very interesting thing that we observe is that humans navigate in a more straight line and navigate in the middle. Some of the agents, the solution that they find is that they go and find a wall and walk next to the wall because it constrains actions. There's less actions if you're next to a wall. They solve the task very well. They sometimes even have a shorter path than humans. But if you look at the agent playing in a game, it's clear this is not a human playing the game. No human would do that. And so right now, the whole purpose that we have of designing these experiments and comparing these and creating a framework for Turing tests of navigation in these games in an Xbox game, so that we can compare that. We have human judges who look at two videos of an agent and a human, choose which one is more human-like, and explain why not. And then you analyze the features that they're naming. Humans are very consistent at knowing what exactly is it in this behavior that wasn't human-like. Then you can go and look and find algorithms that don't do that thing or don't learn like that. Don't do that pluge thing, which is I'm going to go find the wall and stick to it, and then my actions are going to be less, right? So it's interesting. I feel like in the machine learning community, there is the belief that not only is the kluge response not enough, but we actually need we need to observe humans' behavior as well as humans' judgments in order to be able to assess the validity of these algorithms and to improve them, right? And also, can we train a Turing test judge in our classifiers so it can be the judge instead of humans, to have less human in the loop, right? So I don't know. I feel like maybe I don't know. Maybe we should write an opinion piece together. You argue for that side, and I argue for this side, like an adversarial collaboration. Because I feel like the points you're raising are valid points about the way RL is used in cognitive science, and I think that the inverse of them might be true for the kluge throw the fridge at the problem kind of approach of some RL approaches in industry. So I think it would be fun to argue for some kind of a look at both of these and see what is the potential middle ground for these. So I think I'm leaving this conversation more inspired than when I started it. With that,
should we invite Ida? Do you think we should invite some people from the question box? Guess who's at the top? Guess who's at the top of the question box?
Surprisingly, for the first time ever, it's Melanie.
So Melanie first, Jovo, and then and then there's Montrell in the second. Okay.
Yeah.
Okay.
And then we have Abigail. Sam, you probably know the context. Melanie is usually the highest voted question.
Definitely. Should I read it? I don't know where to.
Well, Jovo, are you inviting Melanie in? What happened?
I invited her. She's joining. So, but yeah, I mean.
So she's okay.
How many people can we have in here at once?
6.
Can you invite Montrell in as well then?
Sure.
Hi, can you hear me?
Yep.
Yeah.
Yeah, thanks, Sam. That was a really interesting talk, and this has been a really interesting discussion. So I was interested in your discussion about working memory and its involvement in learning at all stages, and it's always been something that I've thought about in the context of, say, neural networks, that most neural networks, and perhaps it could even be argued all neural network learning that we've seen, doesn't really involve a working memory system of the kind that might be important for human learning. And I think of working memory as being something very dynamic, rather than say simply a LSTM or recurrent neural network sort of, taking some internal representation and passing it on to the next time step. Instead, working memory is very, very much a kind of a feedback system that's dynamic. And I guess my question is sort of what is it about working memory that's so important for learning? And is the fact that neural networks and it's traditionally, don't use this kind of dynamic process limiting to them? Is it responsible for some of their brittleness? And I'd be really interested to hear not just you, but also the other hosts or guests' thoughts about this kind of thing.
Yeah, I can give from a cognitive psychology perspective. I couldn't give it to you from a machine learning perspective. That's a great question. Thank you. I think the easy answer of, at least in the kind of tasks that I've studied in humans, the easy answer is speed. So one of the things you see with learning curves that aren't just kind of incremental trial and error RL is something that looks like a learning rate of 1. Essentially, these learning curves, like I talked about in the slides, that look like these little elevators up to some close to the asymptote, and then maybe a sort of slow hike to a final asymptote. And I think a lot of that is things like hypothesis testing and working memory. And so I think in that sense, RL is, again, using RL in my narrow sense, as Ida correctly pointed out earlier on, but I think RL is, by definition, in these situations, has a lower learning rate. And so that's one really easy answer, is working memory allows you to quickly sort of store a policy for what you should do in a kind of high fidelity but labile sort of format that you can quickly act on. And so the flip side of that is also that it can help you be more flexible. So one of the things that's really hard to do in people is reversal learning, in the sense that it's hard to study because when you give someone a reversal, usually in like a single trial or two, they reverse on you. And if you model that with an RL system with a reasonable learning rate, that's not exactly the type of behavior you would see. But if you imagine someone in working memory sort of just storing a kind of policy or rule about what they should do, and just can kind of flip, oh, okay, that bandit over there is now the bad one, that one's now the good one, you can rapidly reverse. So I think speed and flexibility are the very kind of basic, simple answer to your question. As for like a more complicated contributions, you mean like in terms of task representations and things like that? Is that where you're?
I'm thinking of, maybe memory is an incomplete term, because you're talking about kind of like, okay, it's this passive storage mechanism, but I'm thinking of it as something much more active in terms of, it's a prediction system, it's a simulation system, it's something that's trying to work on models of the world that have already been learned. And
I mean, a way to think about it, maybe, Melanie, if you've ever tried to read Proust, right? Proust notoriously wrote extremely long sentences. Henry James also. Now think about what's happening when you're reading Proust or Henry James, is that you're having to keep reams of sentence in your head to get to the meaning at the end. So in order to actually understand Proust without working memory, keeping all that meaning so that you can keep unspooling, there would be no thinking. So I think your point is very well taken, that unless you can actually construct paragraphs or sentences or thoughts or read Henry James without working memory, it would be absolutely impossible, right? You would never be able to keep hold of all this meaning, and it's not passive, right? Because as you're reading a Proust sentence, right, you're adding as you read and reorganizing it. So we haven't the slightest idea how that works, by the way, right? But you're absolutely right that there would be no complex paragraph length thinking without having a working memory component of the kind you're intuiting. I think you're absolutely right.
John, I want to be really clear that I'm not talking, and I think you'll agree, we're not talking here about something like, a GPT-3, which has these attention mechanisms, which can store, remember words from paragraphs before.
No. I'm talking about working
No,
memory and the
before
active. I'm talking about active. Yes. But let me be very clear. I don't think that GPT-3 does anything that even remotely looks like thinking. So I could care less about it. It's
Right.
completely
So I just wanted to
non-cognitive.
clarify that.
Yeah.
Now, somebody else when I asked the question in the Q&A tab, another Daniel Thinol asks about hot field. There's, I guess, hot field network is all you need paper, which I haven't read, where they add an associative memory to a typical deep learning network. Is that something that can approximate that? I would say no, but, and I'd also love to hear Ida's thoughts on working memory in the context of machine learning systems. To what extent do you think that people in machine learning have really taken what's important about working memory and incorporated it?
So first, I put the hot field is all you need paper in there. There are active critiques of that paper that I have seen. So I could invite some of the folks from the machine learning side. It would be fun maybe one time to have a working memory person from, like, I don't know, from human side and a machine learning person. I feel like this conversation and the way that Sam framed it, and it clashed with my world or the things, the way that it turned out our reference in the outside world to what RL paper, I guess, representatives are. It makes me feel like we should have maybe a human and an ML researcher kind of types of sessions. It would be harder for organization, but maybe we should try. Melanie, asked your question. I pasted a paper in the chat that is by my colleague and collaborator, Matthew Hasknecht and others, and Ricky Loynd. There are people that are at MSR. It's called Working Memory Graphs. So they use more sort of complex versions of it. It's not the same notion as working memory in humans, but it has a notion of attention. It has this notion of self-attention and transformer-based. So it's not just associative learning, and it's not just it's not just an implicit memory or just a stack or just an LSTM. Just wanted to mention this to say that the term working memory, albeit not perhaps in exactly the same way that it's used in executive function and cognitive science, which is my first field. My PhD was basically using fMRI and looking at prospective memory, and then I followed up with models of working memory and episodic memory towards prospective memory. I fully agree with you that it's not one or two processes. However, I just want to highlight with this paper that I shared that there are approaches in ML that have complex set of processes, from self-attention to using sort of various components, multi-head self-attention to reason over a dynamic set of vectors representing observed and recurrent states in order to sort of create a sense of working memory. So it has the approach to keep it in the working memory, as well as an approach to process on it. The simplest way, someone mentioned Hopfield, at least the way that when I was at Princeton, John Cohen types sort of, and everybody else, whether they were in the rodent labs or whether they were in the human labs, the simplest way for simulating a working memory using simplest model were leaky competitive accumulators, or LDA, or LCAs. So you have two nodes at least, and then there is a leak for each of them, and they might inhibit or activate each other. That's the minimum thing. And they can maintain something, or they can compete over something. That's the sort of the simplest thing that you can build a working memory with. And then for episodic memory, you could have Hebbian learning, or you could have associative learning. So that's the way that the 80s, 90s tradition of neural networks in cognitive science and psychology looks at working memory versus episodic memory. The simplest form would be Hebbian learning, associative learning for episodic memory versus leaky competitive accumulators for working memory, right? Where some processing might happen, and then the relationship between them. So if we had just like 3-4 nodes, we can already model a system that has both working memory and episodic memory. You can imagine that neural networks that have like thousands of neuron units these days compared to the sort of the simpler models of the 80s, 90s and that style, it becomes complex to even analyze what is going on there. So my argument in 2017 at the CCN conference in one of the debates, I was saying that, okay, we need to do neuroimaging on our neural networks now to understand what's going on, which is part of the reason I really like theoretical reinforcement learning. Looks at the math and the theory of what is happening in these layers of neural networks. What is the representation learning that is happening here, right? Because as Adam Kepix was mentioning in the chat, we don't know exactly what is happening, and it's not a robust solution either when you just add layers to a deep learning approach. At some point, we need to step back and analyze it. And I think there are people in the ML world, in the reinforcement learning world, in the CS side of it, that are actually working on that. And I think we need more close collaborations between cognitive/neuroscience/psychology folks and ML/RL folks to get it right. Whether our goal is to get human-like working memory or our goal is just to have a good working memory to solve some problems and make more money, whatever the goal is, I think it's important to work on neurally inspired ML, and a lot of people are interested. Sorry, that was a long answer to your question. I'm just going to put that paper again in the chat. Montreal keeps losing connection. I wonder whether we can.
Maybe we can read his question. I'll keep inviting,
yeah, keep inviting him, but maybe.
John, do you want to read his question?
John, you're muted.
John, you're muted.
Much to read. That doesn't help very much to read his question, does it? I guess I could do a mime of some kind. Hold on. I take your point when you talk about machine learning and its simplicity rule. I agree that there seem to be several processes involved during learning of any skill. For example, it isn't clear how reinforcement learning informs us of what may be updated or how the cognitive system updates during after learning. So what's the question? My question is, how would you approach the question of what is updated during skill acquisition? Should we aim to dissect the learning curve? So I guess the question there is, what is the learning signal during a task, Sam? It's not always obvious, right? Especially when there's a credit assignment problem. I mean, I'll give you an example, right? Split belt treadmill training, adaptation to, the work that Amy Bastian and colleagues do, right? What's the error signal?
I think under my sort of being annoying mission here, I think there's multiple error signals, and I think multiple error signals are being learned from in multiple modules. Not to get too Fodorian here, but I would argue that that asking what the error signal is as a singular noun is kind of what I'm arguing against as like as a fruitful question. I mean, it's a good question. Sorry, it's a great question. I just think my answer is to be dodgy and slippery and say, like, I think the answer is that it really depends on which particular learning process you're focusing on.
I think to kind of mention another point of the question that Montreal asked, which is, should we be studying the learning curve or dissect the learning curve? I think it's a really deep point that, again, I don't really do RL kind of machine learning, but do lots of other kinds of machine learning. And the classic papers, if you read them, they often put their final performance, but often do not have the learning curve, so to speak, like performance over number of data points. Sometimes they have learning curves over a number of iterations of the algorithm itself, which is related to the number of training samples it uses depending on the algorithm. But I think the really interesting thing to think about is these learning curves. And some algorithms will learn quickly in asymptote, and other algorithms will learn slowly and do better. And there's lots of theory that you can prove about particular algorithms or particular learning problems, where you can say this algorithm will eventually get the answer right, even though its curve may be arbitrarily slow. And I think that's often ignored for the most part, and that's very interesting and maybe worth investigating further in general, both from a theory perspective and empirical perspective, and then with respect to humans as well.
Yeah, I think that aspect, I think that I mean, I don't know if this is a great analogy, but I think a little bit about like planetary orbits or something, right? Like if you have an object in space that's moving in some way, you need to actually know the objects that are around it, that are affecting its orbit or whatever, right? And so the signal of the thing actually, how the thing actually moves, is one signal, right? Just like our learning curve, it's one dependent variable, but all the things that are influencing it, you know, are hard to see, and you have to take them into account. So I think, to me, like what I would like to see is if you can find a way to take the learning curve and then plot a bunch of other learning curves in lighter colors under it that are generating the thing that's actually observed, essentially the latent things being updated, as Montreal asked about. I think that's at the end of the day, what he asked about what's being updated is exactly the right question. And again, my answer, just like my answer about the errors, is just as there's multiple error signals being generated at once, being read by different learning processes, there's also multiple things being updated.
So, Sam, it's 5:30. I know it's your birthday and you have small children. I wonder how much more of your time we get.
I'll just randomly do an Irish goodbye at one point. If that's reasonable.
Is there anyone else in the chat or from the questions that would like to come in and talk to Sam? I mean, I'm just...
Maybe Abigail?
Yeah.
She has a question that's highly voted. Is Abigail still here? Abigail Person? Is she still here? Irish goodbye, Melanie, is when somebody just leaves without saying goodbye. It's basically no goodbye.
Is that related to an Irish shower?
What is an Irish shower?
I think an Irish shower is you just put deodorant on and go.
It's what?
You just put on deodorant and go.
That sounds kind of...
The proper term is a French exit. That's how it is. It's a French exit when you leave the party without telling anyone that you've left.
Right, proper wear.
Yeah. Yeah.
Hi, Abigail.
Hello. Yeah, so I had a question that revolved around this idea that has been developed by Sam, by John, and possibly the others on the panel about the competition for error or errors by multiple learning systems. And I don't know if you guys can hear me, but I'm kind of frozen. So
We hear you. You sometimes
Okay.
get frozen, but not entirely. But we
Okay.
perfectly hear your voice is fine.
Okay. So the fundamental question is whether there is some overall learning rule that all the learning processes are participating in solving cooperatively. And the way that I would appreciate sort of this idea becoming concrete to help me out is to think about a relatively simple associative learning structure that takes some inputs and produces an output to solve some kind of problem. If the multiple learning systems are all operational and the inputs keep changing to this associative learning system such that it needs to keep changing its outputs, what are the ideas about the steady state behavior of this system? And would a convergent solution or a solution that actually asymptotes suggest that there is in fact some kind of larger rule or set of rules that are being attempted to be followed, problems that are being solved. I don't know if this makes sense.
So if I might have to ask you a clarification. So are you saying like, are you kind of getting at that the kind of existence of the steady state asymptote that we see in lots of these tasks? If there's multiple processes, then that probably means that there's some kind of like equilibrium having been reached between those processes, because if there isn't an equilibrium, why would we not see sort of one system come in and one system come out and the asymptote like oscillate or something like that? Is that kind of what you're asking?
I don't necessarily think that we have to interpret the asymptote as being evidence for this. I think it's not necessarily not evidence. It could be, right? That there is some stabilization of the brain's solution to a given motor control problem. I guess my question is, if it is the fact that there are these multiple learning processes, how do they cooperate? How do they know whose role is what? And what is the overarching goal of the system, if so?
I see. I'm going to be slippery and dodge that question too. I mean, I think there's cases where you can clearly see people's behavior looks like systems are not cooperating towards the same end. John showed this very nicely in a paper 15 years ago, right, where you can essentially get people's motor system to keep driving learning, even though performance in the sense of the feedback going where it's supposed to go being perfect, right? And that's just because there happens to still be this mismatch between movement and feedback, and one system's really angry about that and another system doesn't care.
Does that remain the interpretation today? I've been trying to follow the recent papers on this year.
Yes, it does remain the interpretation, actually. Yes, it does seem to be that there are two kinds of errors that can be in conflict. I mean, I think Sam's point that they sometimes, let me just give you a much more concrete example, right? There was a wonderful experiment done, a stroke model in the monkey, right? And the monkey had to remove pellets from food wells. And it came up with a compensatory strategy because it had damage to its corticospinal tract, so it had to do something other than a precision grip, and it could get to some percentage performance ability. So it fell into a local minima, basically. Now, if the goal were to actually, in the end, have a higher level of performance, it should have actually tolerated worse performance in the short term in terms of getting better learning performance. So kind of almost like learning discounting, right? Now that's why we have coaches and trainers, because they have to teach us learning discounting. We have to actually practice and be bad for months, if not years, because eventually we'll be good. Whereas if we just go to the tennis court ourselves at the weekend, we'll come up with something good enough. It will be better in the short term, but we'll never get to the high performance in the long term. So these conflicts are happening all the time. Now, one way that one could think about it is that you can have goals over different time scales, and those goals have to map onto different learning processes. And sometimes we just don't know, right? I mean, I think there is no master goal that wins, right? The only way that monkey finds the proper solution, by the way, is having an experimenter or a therapist slapping them when they try and do the compensatory response. So it's actually very interesting, right, that you have to set up the conditions under which one learning system will get its best debut versus other situations where a simpler system will, but you'll never reach what you could have done had you used another one of Sam's systems. So it's like a messy democracy, right? There is no absolute ruler. It's fascinating.
As long as it occupies the capital, I guess.
Wouldn't you agree? And I think, Abhijit, your point about whether there's been a lot of debate about it, I know what you mean. I'm very much aware of these, and this is going to get too specialized. But I have to say that I don't think the notion of two different types of error has gone away. Wouldn't you agree, Sam, that we still agree in the difference between target error and prediction error?
Yeah, I totally agree. I think they're dissociable. I think there's Hebbian learning on top of that that's adding noise to the mix. So yeah, with no error signal, in other words, too, right?
Anything else you wanted to add? Oh, go ahead.
Yeah, I'll put one button on what John was saying that I think we shouldn't get into because it's a separate conversation you guys have talked about. But I really think at the end of the day, I tried to avoid this in my talk, but I really think these bring up questions of modularity, and really thinking about, you have to sort of, at the end of the day, if you buy the fact that the learning curve is composed of all these different processes, and whether that's being properly recognized or not in AI or in psychology, then you have to really ask, like Abigail just did, if these systems are operating modularly, if they're encapsulated, right, like what Fodor would say, those questions start to, you have to deal with them. You have to deal with those questions. I think there's really good work in perception on those issues.
So I think that that comment gets at sort of my underlying concern, which is that, as the brain is not ever isolate, like no part of the brain doesn't hear from another part of the brain. If cortical, inputs say to the cerebellum and it's, let's call it the sensory motor, estimator, are constantly changing, upon what is it, making its estimates, and how does it figure out what it needs to do that the cortex isn't going to do?
Yeah, again, I think I like that question, but I do think this I go back to the decerebrated ferret. And I really think that there's lots of examples where a system did happen to evolve. It's a little machine that evolved. And that even the fact that it is connected to the rest of the brain, or the rest of the cortex in that case, is useful and interesting, and we're studying is something I'm interested in. But also the fact that it can operate independently, I think has huge implications for thinking about how isolated these systems really can be.
Yeah, and I think in the case of the delay eyelid conditioning task that you mentioned, I think the fundamental question that I would have is, how does that system operate when the CS is constantly changing because the cortex is always doing something different? How can it handle that?
I think it's screwed, right? Those I think when you lose those kind of more complex behaviors, I think, yeah.
Thank you.
And also, one more thing, Abby, I would say is, if you watch, a patient with alien hand syndrome, for example, when they have an ACA infarct that leads to a callosal disconnection, and they literally will reach for something and the other one will try and stop it. So you actually have one person's two hemispheres fighting over the goal. Where is you? Right? So in other words, that's a profound demonstration that there is no you, right? It's spooky.
Yeah, I think the split brain stuff, Roger Sperry stuff, amazing. Yeah.
Yeah. Thanks, Abby.
Thanks, Abby.
Great question.
Hi, Meredith.
Hey, Meredith.
Yeah.
Hello. Good to see you all. Happy birthday, Sam.
Thank you.
So
I'm enjoying my cupcakes.
Yeah, well, yeah, somebody else apparently is going to eat them. Thanks for getting me in. It's fun. I once in a while manage to watch this, and I always love it. So I have a quick question. I like to understand things principally, and I'm not a complexifier generally. And I feel like you're advocating for complexifying things. So my question for you is that if it's inherently messy, learning of all kinds, and if we go by John's example that no matter what you do, simple tasks in the lab, real ecological situations, everything is going to be complicated things of many things, are we kind of like just giving up on understanding principle way of what learning is, or actually are there principles that we can understand? If we're going to come up with a laundry list of learning schemes, and for every task there will be a bit of each of them that will contribute to all sorts of tasks, what's the goal of studying this system to begin with? Like, what are we trying to learn?
Easy question. No, I mean, I think the part I'm noticing thank you, Murda. I mean, your question in the chat saying, can we hope to learn other principles other than the principle of things are messy? And I actually think the principle of things are messy is really interesting and actually worth itself being studied. So that's a dodge, but I do think that, like, I don't want my point. I kind of framed my point as being I'm just going to be annoying and say that, look, there's always going to be all these different qualitatively different things happening. But I think that is itself a principle. I just want to make that point first. And secondly, my answer is, I don't know, get into art dealing or something.
Well, so the reason I say this
No,
is that, no, I know you're joking, but the reason I ask this is that, there is a level at which we can study learning, which is at the level of, synapse and molecules. And I guess, many of us will say, no, that's not the right level, because principles will not emerge. It's too complex, it's too messy, and, you're really not going to be able to learn something. There's homeostasis happening, their synapses are changing, brain areas are changing. Everything is being adjusted. So you're not going to learn anything. And we adopt the principle of going for abstractions because things hopefully will present themselves in a more easily digestible fashion. But if we come all the level of abstraction, and then you're going to say again that no, things are really messy and you're not going to understand anything, then why don't we just go to deep networks and just train them to do tasks and forget about trying to understand them?
+1.
Yeah, Mehrdad, I would say there are two answers to your kind of question. One is, when you say there are many processes and then you just have to weight them differently for a real life task, I don't think, going from Cummins, a philosopher, that it's wrong to identify subcomponents which one feels are relatively pure, right? In other words, I don't think it's wrong to talk about target error or sensory prediction error or reward prediction error. So I don't think it's completely lost. I think that, wouldn't you agree that if you could parameterize one task by weighting particular learning processes, that wouldn't be the end of the world, right? In other words, if you believe in sort of decomposition of complex systems, there's always a sub-level of components that one can think with. And I agree with you, it's not going to be synapses or individual cells. So I don't think we're being nihilistic. I think you just have to, what I always tell people is distinguish tasks that are more like assays, if you can build assays. For example, finger individuation, right? You can test finger individuation in a patient, or you can test dynamometry strength. But dynamometry isn't a task. Finger individuation isn't a task. But you think that those components are used in a real life reaching movement, for example. So I don't think all is lost. It just, maybe the components that you divide something into are more abstract than you would like. But I think decomposition into subcomponents, which are fairly robust, is very much still on the cards, I would say. I think that's definitely possible. It may be that they're not, that the components themselves will never be subsumed by one computational theory. In other words, it won't be state space models for error-based learning and reinforcement learning algorithms. Maybe there won't be a master algorithm that describes all the components that make up the task. So you'll get empirical decomposition, but you might not have one theory that explains all the components. That's what I think is going to happen. So if you're willing to have empirical decomposition with fairly robust objects, I think Sam and I would say you can get there. I'm not sure there'll be a theoretically universal principle.
I guess, first of all, if others have anything to add to that, I don't want to.
I want to say no one is looking for, I don't know what you mean by universal principle. Like, it seems like all of a sudden the goalpost moved to somewhere that nobody was there.
Well, Ida, just give an example to your point. I mean, when adaptation tasks were first being studied, there was a belief that you could fit a particular kind of model based on a particular kind of error, and it would fit the learning curve really well. So one could be lulled into the sense that one process that could be parameterized could capture almost all of the variance, right? And it turned out that that was not true. So sometimes you can have a model that is theoretically quite compact and fits a lot of the data, but it's a wrong fit. And I think that's the point, that you have to sometimes your model is more universal than the empirical components. That's
So
all I'm saying.
So it sounds like that was just not the right model for that particular thing. And a part of science is coming up with theories, and then if it doesn't fit, then you find an alternative theory and find a better model.
But there may not be one theory. That's what I'm saying.
It's tricky. It's tricky because I think a clever scientist I think can come up with a model that's complex enough to explain a learning process without having to deal with the frustrating fact that they've lumped qualitatively different things together. And that doesn't mean it's a bad model in the engineering sense. It's probably great, right? But a clever person can probably find a way to explain a lot of different learning with a singular process if the data are just like a learning curve. I mean, I think to Mehrdad's question, my one button on it, and I'll stop. I think you can sort of think of it as like a scree plot, right? So if you've explained a lot of the variance in the behavior and you've properly acknowledged that there's multiple components, multiple principal components that are contributing to that variance, then I think you've done a pretty good job. And I'm not being a nihilist like John said, that because you're not explaining 100% of the variance, you're somehow missing huge, principally important things. You can acknowledge that there's some other stuff going on. But I feel like, we always look for that one component, right? And that's my main point, is really just like, do the scree plot, right? Well, maybe there's a couple other things and maybe they're not talking to each other.
No, let me just give one more example to Mehrdad, right? I mean, Jeffrey West, I think I've talked about him before on this salon at SFI, has come up with these scaling laws for all sorts of things, like villages and towns and cities, that in fact there are these invariances in terms of miles of electrical cabling and walking speed and number of traffic lights, sublinear scaling laws for tell me how big the town is and I'll tell you how many gas stations they have, right? These laws that go across, but there are other things that don't, right? So you're not going to come up with a universal theory of a capital city, right? That there are some things that are scale invariant, and other things like Alvin Ailey dance troupe in New York City. Who knows why they're in New York and not in London, right? So all I'm saying is that you're not necessarily going to get, there'll be some things that you can universalize and other things that you just can't. They're just messy combinations.
I don't know what kind of universal rule would require that a dance company would be in London. I lost the connections there a little bit, John.
I'm just saying that there's going to be, I'm just saying that there aren't going to be theories of everything.
I'm not sure where this straw man came in, but I'm just going to wait for Mehrdad to respond.
Yeah, I also kind of understand, this kind of putting the goalpost there is helpful, John, because it kind of clarifies that the search for a universal principle is not the right path to go forward. But I don't think also many of us will expect a universal principle of the form that will encompass the kinds of examples that you just presented. But what I was trying to not really necessarily push against, but I think when we're dealing with biology, and Sam is particularly interested in that, it's not just a machine learning question. I think that the notion of scree plot is everywhere. And to try to use that as a way of saying, like these systems are complex, I think I can do that for almost anything you like in biology. And I will be able to say, no, you're just not doing the right thing. You're not explaining the whole bunch of the variance, and therefore those sort of theories or abstractions are not really great. And the field is kind of being misled by thinking that way. You rather should just consider everything is everything. And I think that's to some extent will be true. It's a truism in some sense, right? The normative principles are mostly for us. There is no homunculus sitting in the brain saying which system should learn which task. You present a task to a subject and the brain goes at it. And some parts of the brain in some individuals, based on some genetic factors and some previous experiences, will turn out to take on the task a little bit faster than some other parts of the brain. And that other part of the brain will slowly give up. And the part of the brain that finally brings the zero to the error or brings the reward to the maximum will stop the learning. And maybe not. Maybe there will be also additional learning that happens because of all sorts of other, longer term things that have to go through homeostasis. And coming up with that kind of a solution for explaining brain, I don't think it's nihilistic, but I think it kind of misses the point of looking for principles. So although I agree that this sort of being cognizant that there is a scree plot and we're not explaining everything is really important, I also think there's real value in sacrificing variance for simple explanations that are not perfect. And I just wanted to say, there's a reason that the two system in cognitive science took over. I'm not saying it's correct, and I'm not advocating for two, but I'm just saying this notion to bring small systems and saying for certain types of behaviors, certain types of learnings are more important. Actually, there's value in that. I just wanted to kind of like say, pushing all the way to the 100% variance is what deep networks are trying to do for vision, right? This is just let's just explain everything, and that's the only way to come up with predictive variance of 100%. I feel a little bit unsure that that's my taste for what we should call a principle.
I mean, and just Mehrdad, to your point, I mean, there's so many interesting things you're bringing up there, right? When you say value, right, that's a normative statement, right? So, and then it leads to the notion, well, what do you mean by that? Are you saying that sometimes it's better to have understanding than prediction? It's absolutely correct, by the way, that they can dissociate, right? You can feel like you have a sense of understanding. It's actually not accounting for as much variance, but it has epistemological satisfactory effects on the brain, and maybe you can think up new experiments that you wouldn't think up otherwise. But I think it's just very important when you say there's value in searching for principles, even if less variance is accounted for. Well, value in what sense? Generalization, new experiments, satisfaction. We have to say what we mean, right? Otherwise, it sounds a little bit hedonistic. Do you see what I'm saying?
Yeah. So totally, I think it's the main point of this value is that if you think about a coordinate system in which one direction is sort of predictive variance to the end, and one direction is sort of this satisfaction that comes from principles, we want to optimize in this entire space. But the thing is, science is hard, nature is hard, and we don't know how to get to that end point. So taking a specific way of thinking and trying to predict variance more and more might hit a dead end without we realizing it. So the notion of understanding, the value of it is that you allow yourself the imagination of combining modules, principles, and things of that kind, and then they may be wrong, but they leave you with an open space of exploration of hypotheses, generating new experiments. And that's one way of driving progress.
Oh, I would just answer that I thought that's what we were doing. I actually thought that finding the right subcomponent objects to think with, to combine them, without combining all of them in the scree plot, right, getting all the eigenvalues, right, I thought that we'd end up agreeing, just like in your wonderful piece that I cited to you before, when you talk about the cogs and the springs in a clock, to explain a clock. You have implicitly stated, Mehrdad, that those are the right objects with which to think about the clock with, right? Springs and cogs. And so all we're saying is the springs and cogs might be different learning processes.
Then I guess the question becomes a more targeted and nuanced one, which is, what are the ones that we should be thinking about? If it's not the slow and fast system, but we're also not going to say it's this complex mess that we don't understand, then we can be a little bit more precise in what we're saying. So, okay, it's not 1,000, it's not 2. Yes. But we want to really have some explanation at some level. And I think this comes to what Ida was saying at the beginning, that there is a clash between going for, like a system that maximizes to nth degree without really thinking about principles, and a system that brings 2 and sticks to 2 because that's easy to understand. So I guess if I were to ask you, Sam, you, John, Ida, Jojo, like what is this space of limited but sufficiently rich, points on the scree plot that we're going to take as a good starting point to net?
So I'll give you a tongue-in-cheek answer to. There's a wonderful book called The History of Philosophies, which is a 500-page book on how academic disciplines evolve. I recommend it to everyone. It's kind of sobering book. And in that book, it turns out that in any subfield of human endeavor so far, there are about 6 experts, right? It's fascinating, right? You can do the experiment yourself. Name more than 6 people in your field that really matter to you, right? Look, it's fascinating. So maybe the answer then is 6. And if I remember, actually, in Sam's plot, when he had the different bits, I think it was about 5 or 6. How many was it, Sam?
I think it was 6. I think it was actually.
So I think the answer is around 6, my dad.
Or maybe it's your working memory limit.
Yeah,
the
that's
whole
right.
stuff
Yeah.
too. And maybe some millennials have higher working memory limits. I don't know that, but it seems like some of us are inclined towards complexity, but we are inclined. I think John, you said something wonderful that I actually put in the chat, and I feel like it's very congruent. As much as this conversation right now sounds like we are all on different sides, I think, John, you might be closer to Merda than I think myself than it seems right now. You said something. You said, it depends on how much you believe in the composition of complex systems. It's true, things are a mess, but the whole point of our capacity for perception is to decompose it, right? And the decomposition doesn't follow necessarily the rules of our working memory limits or how we can visualize things. I think or how much our ANOVAs can tolerate and these kinds of things, right? So at some point we have some methods that are multivariate and they can handle multiple principal components and then run a multivariate analysis on the principal components, etc. I think we might not necessarily need to have also 6. What we need is a good algorithm for decomposing. And by algorithm, I don't need a program that you write, but a scientific algorithm, a method.
I do think Merdad is, a scientific algorithm, right, is what you're saying, Ida, that there may well be a scientific understanding algorithm that we may be sort of all spinning together and beginning to converge on it, that we might actually agree more than we think that we're getting there. Right, something like that, right? Yeah, exactly. I mean, Merdad, I think your point about understanding is a very deep one, that we as scientists, human scientists, have a requirement. And it has to be manageable, whether it's what Ida said, visualizable or articulable, but it's probably not as big a subspace as we think. It's probably a sweet spot. And I don't think it's 6, I think 6 is interesting, but it's not a lot if you want to keep it in your head.
Yeah.
Can I ask you 6 people a question about this, which is, I mean, this screen plot analogy I think is really helpful for me. Where are we? Like, you choose your task or whatever. I know Bruno wrote this beautiful paper on visual system, like what do we do with the other 85% of the variance? Like, for the kinds of things that you are studying, what fraction of the variance can we explain now with the simple models? Are we at 15% or 85% or 1%?
I don't know. I'm sure the answer is it depends, so I can't be helpful. But I mean, I would say for certain things that, like what I study, like these simple sort of motor learning tasks, I think we've done pretty good job of narrowing down I don't know, John, 4 processes. And I think that's one example where I think we've gotten to probably 85% of the variance. But I think it just depends on the system, I guess. I don't know, to dodge. But.
Jojo, I would say it's the problem is we're really early in the system. Learning has been really hard, and at least as far as I can see, where the subfield that I have looked at and carefully kind of studied, we have done so little that we don't know as we move forward any inference we have made about the form of the scree plot, how it will kind of reshape itself. So I think it's really difficult to know. And part of it is evident in machine learning. Like, as soon as the machine learning sped up in terms of doing more real tasks, it seems like it's exploded, just like the agent that Ida showed. So it's not clear to me that as we move forward in humans, I mean, the hope is that the scree plot will not explode, but I just don't think the data is there.
I just want to add one thing that I mentioned in the chat, but there is a field in theoretical reinforcement learning, and Princeton's computer science department, in fact, is very strong in this, which is analyzing mathematically what happens in deep learning algorithms, analyzing the representations, finding if there are guarantees that a particular system is going to solve a problem or not. So there is the empirical approach, which is chasing some specific benchmarks, pushing the progress forward. It's not always stable depending on the seeds that you have. And I think it's very fascinating as well. Like, I think it's awesome that it's happening. But there is also this other side that is I guess it's the fast and slow of reinforcement learning, is then analyzing things, going to the whiteboard, doing the math, and then seeing what actually is happening in these layers. What are the components? How can we analyze their interactions? What is necessary or guaranteed to solve a problem? Under which assumptions? How simple can we go? At which point are the simplification of the assumptions not going to work? Which approach is going to be too, it looks fantastic, but it's going to be too slow, so it's not going to be in practice effective. Which approach is not robust? I think it's important that there is both of those two things. And that's another reason that I think there should be more dialogue between neuroscience and various types of ML, including reinforcement learning, and not just the empirical things that you see that solve some benchmark, but actually the more boring, the math part. Because I think that's actually the part where you can see, why does this thing solve it? And what is in principle the component that a particular part of the network is giving us? We don't always have answers. Sometimes you just don't know why adding a particular layer is really improving things and why taking it off is going to decrease it. It's funny. After something has learned, you take some things off and it's still doing perfectly. But if it starts learning with the minimal amount of layers, it's not going to get there where you can all of a sudden sparsify the number of layers or neurons. And this is a challenge because a lot of people want to obviously reduce the amount of compute that these deep learning approaches have. And it's a mathematical problem that actually we saw a talk about it, where how far can you sparsify from the beginning as opposed to a little bit later? It seems like early on you can't be that sparse, but later you can be. Which the time when I was seeing this, I was like, oh, I wonder whether this person has talked to developmental neuroscientists, because this is what happens in the brain. Like, there is a lot of pruning that happens. Interestingly, this is the topic of pruning in neural networks in computer science that they theoretically analyze. Very similar to the topic of pruning in developmental studies, of the pruning that needs to happen in brains. But I feel like there's not enough sort of workshops or sessions where you bring people from the both sides and they present their works and, to look at the connections there. I think there might be a little bit more method to the madness or method to the messiness, as Sam might be giving it credit.
And I would also say, Mehrdad, to you is, when you ask, it is difficult sometimes, and maybe Sam can't answer this, is what are we after? Right? What are we after? In other words, when are we done? In other words, what is it that you want? Right? In other words, you can assume that you can just do what Ida's sort of saying, which is do some sort of informed task decomposition and assume the nervous system is infinite in its capacity. You can do that kind of work where you say, what is the way to think about the task, and be entirely normative, and then see if the nervous system does it. Or you can go the other way around, which Ida's also talking about, which is, well, how constrained is this system? What does it have? And what can it actually do given this task? And you can go in both directions. But I think, and you and I have discussed this before together, is what do we want, right? In other words, I think that's actually difficult in a biological question like the work we're doing, is what do we want the answer to be, right? And I don't think it's easy to me. Daniel Wolpert once said to me at a dinner 10 years ago, if an alien came from outer space and had all the answers, what would you ask it, right? And it's not that easy to come up with your magic set of questions. The alien's going to be there with you an hour. This is all you've got. Get your questions right. What would they be? Do you see what I mean, Sam? What are we after?
So I'll just say super fun, everyone. I know there are lots of interesting questions. I have lots of things to ask and lots of things to listen, but I'll go out so that you can invite others. And thank you for this. It's fun. It's more food for thought. I'll start thinking more about the middle level of question of learning is a really fascinating one. So I'll keep thinking. Thank you.
Yeah, we love having you. We
Thanks for
hope.
joining.
Thanks, Mehrdad.
You have to come every week now.
Yeah.
Yeah.
Ciao, Mehrdad. Bye.
Maybe we can end with one last question that Ella asked, and I think that it was a good question. Ella was a little camera shy, but we can ask it for them. They ask, in adaptation tasks, the learning gains are transient and don't persist over time. What do these, oh, things moved as I was reading. Okay. What do these temporal gains indicate? Is it learning or just a sign of some temporal working memory effect? So again, in adaptation tasks, the learning gains are transient and don't persist over time. What do these temporal gains indicate? Is it learning or just a sign of some temporal working memory effect? This could be equally for John, I guess.
Yeah, I'll just answer a little bit. I think it's a great question. I mean, I think that there are aspects of learning that do persist over time, right? So the question is if you can isolate what are the parts of learning that do persist and what don't. I think your intuition would be borne out that the stuff that doesn't persist probably was that transient, maybe strategies held in working memory. But you know, there's definitely evidence John's lab had for these type of tasks where you can actually give someone, I don't know what it was, John, you can correct me, 3 or 4 trials of this task, and actually the next day they have savings. They learn a lot faster than they did on day 1. So there's even with just a few exposures, you can get persistent behavior. But then I think you're right, and of course there's also transient bits of it too. So I think this just brings in the same, oops, I had an ambulance, the same sort of issue where some parts persist and some don't. John, do you have a?
Right. I mean, it's interesting that we've done experiments where people have done, you know, one of these rotation tasks, and I didn't publish it, but I had people come back a year later and they showed savings, right? It's bizarre, right? In other words, I mean, it comes to this general idea that no one ever forgets anything. It's just a retrieval problem, right? That what do you need to get someone to retrieve what they've always known? So
The tagging problem.
Yes, the tagging problem. So yeah, it's you know, I think what's so lovely about what you presented, Sam, is you're looking at a particular model system which is interesting in its particularity, but you're making general statements, right, about how much decomposition can we get? Is there some rule of decomposition, as Ida was getting at, that we don't know yet, right? That maybe, you know, there's a limit to how much you can break a task down in a mammalian brain. I mean, it's just very deep issues. Right? Yeah.
On that note, we thank everyone for a fantastic discussion, and it's funny. It always exceeds what I expect. I don't know how this happens. It's possibly that the company is so awesome that the collection of our parts is less messy than each of the parts. See what I did there, Sam? Sometimes you put the right components together, and instead of mess, you get structure and awesomeness. So. Yeah, so we thank Sam once again.
And I hope it was a good birthday, Sam. I hope it was worth it for you.
I'm very sad that you can't have a drink for your birthday.
I'll have a drink for each of you. I'll have an extra drink for each of you.
If this was Princeton, we would have gone to the Dinky at this point.
Yeah, right.
With that, I want to also thank Kanaka and also Brad and Claire, who have been in the chat and behind the scenes. And thank you everyone who asked questions, Melanie and Mehrdad and everyone else. And happy birthday, Sam.
Bye, everybody.
Thanks, everyone.
You.
Bye.
Thank you.
Weekend.